Okay, so this is basically a continuation of the last lecture on the two-dimensional Fourier transform, okay? And so fundamentally, the goal of today is just to kind of show you how to think about things in the Fourier world when you're processing images. So we kind of want to look at the spatial filters that we defined in lecture 6, I guess, and then think about how to apply the Fourier transform we learned about in lecture 7 to do frequency domain filtering, right? And so the idea there is that if we're looking at a kind of frequency domain instead of a spatial domain pipeline, just like in the one-dimensional world, what you'd say is, okay, I've got my image over here. I would, for example, do the 2D DFT, and that would give me some sort of a frequency domain image. I guess I fell into the same trap I did last time. Let's call this like I prime of UV. Then I would apply a filter in the frequency domain, H of UV. Then I would have some new image. This is basically going to be like the product of the Fourier transform of the image and the Fourier transform of the filter. And then I would put that through 2D inverse DFT to get back some output image. Right, so that's basically the way that we handled one-dimensional DSP frequency domain filtering. It's the same thing in images, okay? And so what I want to focus on today is mostly, we talked a little bit last time about what do the Fourier transforms of real-world images look like, what should you expect to see. And so just to refresh your memory, generally we expect to see, frequency domain content clustered around the DC value, which we kind of shift towards the middle of the image to make it easier to visualize. So let's think about today, what are these filters here going to look like in the frequency domain? And as I mentioned before, while it's true, so again, spatial domain convolution is the same thing as frequency domain multiplication. Right? And so convolution is basically the same as filtering in the spatial world. Okay? Okay, so let's take a look at some filters in the frequency domain. All right, so I wrote myself a little function, and this is kind of like actually one of the things that I'm asking you to do on the homework. So if I see what I have in this directory, I wrote a little function called idealFilt that basically lets me generate a bunch of different kinds of filters. I can generate high-pass filters, low-pass filters, Gaussian filters, and so on, and then I can filter an image with it, and I can see the results, right? This is just to make my life a little bit easier. So, so let's choose an image. Not sure what images I have here. Let's use my valley image from last time and make that a grayscale image. Okay. Bless you. Okay, so here's my image. And warning off so I don't get these warnings. And just like last time, what I can do is I can look at the FFT of this image, and kind of what I did was we said, okay, there's a cascade of things that I do in MATLAB to make this visualization easier. First, I take the FFT2 of this image, and since it's a complex number, I take the absolute value of that. Whoops, absolute value. And since it's got a very big value at DC, which is the sum of the image intensities, I take the log of that to make it a little bit easier for me to visualize. And then because it's got a, since the highest frequency is in the, or since the lowest frequency is in the upper left-hand corner, I do this FFT shift to make the middle frequencies look like low frequencies. So here is the Fourier transform of that image, right? So again, we kind of get this general, high frequency content in the middle, not much action happening at, low frequency content in the middle, high frequency content at the edges, and not much is happening there. Again, remember that since this is on a log scale, there's actually very little stuff happening around the edges and lots of stuff happening in the middle. If I was to plot this without the log scale, and let's see, I guess what I would say is, I was thinking about this the other day. So let's take my output as the FFT2, the absolute value. So this thing is going to have some huge value at DC, right? So I'm just going to, for the sake of argument, zero that out just to make it a little bit easier to visualize. And then I'm going to look at the FFT shift of this guy now. So on a linear scale, let's see, I don't know why that went. Let's see what that is. There's still some pretty big values here. I'm actually curious to know if I were to histogram this. Right, so there are still some big values over here. Many of the values are pretty small. So I think it still makes sense to do it as a log scale. But that's why if I were to show this as a linear scale, these values out here are just dominating things. So if I were to just say, show this output on a scale of 0 to, let's say, I don't know, 500,000. I'm just kind of guessing here. And I guess I want to FFT shift this. Right, so here's maybe a more accurate representation of the linear scale of where the frequencies are, right? So really, most of the stuff is clustered in the middle, and there's very little high-frequency stuff at all, right? So you shouldn't be fooled by the log scale thinking that there's all this stuff happening out in high frequency. I mean, a lot of that stuff is really, really small, okay? Okay, so let's go back to my filter, and I have to remember to myself what I define this filter to be. So basically it takes an image as the input, and then I specify some band edges, and I say what type of filter I want. So I'm going to make myself an ideal filter that is a, so let's take a look at this frequency domain again. So I don't know why, I guess with imshow I don't get axes. So what if I were to do just image of out, for example? That's even worse. Well, I can still get a sense, though. So kind of what I'm trying to get at is that I want to know how wide is this middle area here, right? So I mean, it looks like, in the frequency domain, I can try and grab a couple points off of here. So let's see kind of how wide this circle is. So it's probably about 20, units wide in the frequency domain. So let's suppose that I make a filter that is like a 20 by 20 low pass filter. Okay. Whoa. The usual mistake, rookie mistake. Okay. So what are we going to see here? Well, here's my original image. Here is the Fourier transform of that image. Here is an ideal filter mask, which is basically saying, pass all the frequencies inside this box, cut out everything else, okay? Now, when I apply that to my image, what I'm basically doing is I'm just preserving all that stuff inside the box and throwing everything else away, right? Now when I take the inverse DFT of that, I get this blurry image, okay? So I mean, this does look kind of like what I expect to low-pass filter something. When I low-pass filter something, it should blur out, right? Because what I'm doing is I'm losing these edges. I'm losing the high frequency stuff. And in fact, here you could argue that I've blurred out, a lot of detail. And then this is just a picture of what the spatial filter looks like in the spatial domain. So you can kind of see that, I want to do this thing. First of all, I want to make this bigger, sorry. So if I were to think about the filter as a, matrix of pixels, it's going to be high in the middle and low everywhere else. I'm trying to figure out why I can't make this guy bigger like I want. So it kind of looks like, a filter that has got big values in the middle, small values at the edges. And there's one thing that you notice immediately, which is, why does this image look so crappy, right? So, here, not only is the image blurry, which we kind of expected, but there's also all of this like weird wavy stuff that I've introduced in the image. So if I look at the original image versus the filtered image, like there's definitely some weirdo artifacts that are coming, like it looks like almost there's these lines that are rippling off the top of the valley, right? So we're going to talk about why that is in just a second, but you can maybe guess why that's true from looking at the spatial filter, so that what the filter does in the spatial domain. So if I rotate this around, you can see that in the spatial domain, this is not like a smooth roll-off of values. There's instead this kind of bumpiness, right? And this actually kind of relates to, I got all these windows open. This kind of relates to something that, we were talking about at the end of class, Janet and I, about what do we expect to see when you take a pulse in the spatial domain, so this is spatial domain, and convert it into the frequency domain, right? So what do we get when we take a pulse in one world and convert it to the other world? Sinc function, right? So in general, we know that a pulse in one world corresponds to a sinc in the other world, right? Now, it turns out that this is not like exactly true for digital signal processing with finite length signals, right? So remember that we don't really have this pulse actually in the frequency domain. What we have instead are kind of like a pulse train, right? Because there's this kind of implicit assumption that things repeat periodically, right? So kind of what we really are doing is we've got this thing in one world, and it turns out that what you get in the other world kind of looks like what you get if you alias a sinc together with itself a bunch of times. So kind of like, you kind of expect to see something like this, where this sinc kind of repeats itself. Because a normal sinc function dies down after a while. Here it's like we're kind of taking this guy and shifting it together and adding it up, right? And so kind of this looks like, this is kind of like a periodic sinc. And actually what you could show is that the actual form of this function is like sine something over sine something. So instead of sine x over x, it's like a sine over a sine. So we don't need to belabor the point of exactly what the formula is, but fundamentally that's exactly what you see, right? Because if I look back at my function here, I can see that things are clearly, ripply instead of being smooth, okay? Now, as I change the size of the filter, I should expect to see kind of a different, what's the right word? Different period of the rippliness in the frequency domain, right? So let's suppose that I made my filter a little bit bigger. So let's suppose that I used a like 200 by 200 low-pass filter, okay? So now, for one thing, if I look at the original image versus the filtered image, it really doesn't look that much different, right? And the reason that we know it shouldn't look that much different is because this is the effective filter in the frequency domain, and we already knew that the vast majority of the image content was contained within a smaller rectangle, right? And so in some sense, this filter doesn't have that much visual effect on the image. And if I think about what I see in the spatial domain, there is some rippliness, but it's certainly not as visually pronounced as it was before, right? So like it's kind of hard to even rotate this around to show you the rippliness. All right, let's see here if I can get this to be something. Yeah. I can't even really do it that well. I mean, you can kind of see that it's not a smooth decrease. There's still some rippliness here, but it's definitely not as visually pronounced, and it also falls off much faster than in these other one. And kind of conversely, if I were to really try and filter this guy down even further, like say I have a very aggressive low-pass filter, here, I mean, at this point, I've blurred the image so much that, frankly, you don't even notice the rippliness because you just see a big blob, right? And here is the filter. The filter has obviously got some more visible ripples in it, right? So here you can really see how bumpy this filter actually is. This is actually a better illustration of seeing how that filter kind of rolls off, right? Right. So that's the kind of basic idea behind. So I would call this in the frequency domain. I would call this like a box filter, right? Because all I'm really doing is taking a box out of the frequency domain and preserving the middle part and throwing away the rest, right? Okay. So let me pause and ask any comments or questions about what's happening here. So another thing you could do instead of a box is you could make kind of a circle instead, right? I mean, instead of having a box, I could have a radially symmetric filter. And so my little MATLAB command that I wrote allows me to do that too. So if I just provide one argument, if I recall correctly, so here, I've got, again, this is now my cutout in the frequency domain, and I preserve this part of the image, and then I get, the output image. And again, since this was already the highly generous low-pass filter, not much visual change. I mean, you could argue, if you really were to think about it, right? So for example, let's look at, let's look at like this part here and this part here. So I mean, I think that, here you can see the smoothing, right? So there's definitely higher frequency stuff that has gotten filtered out by this filter. But for the most part, you can't perceive this in the, large details of the image, like the side of the cliff and so on. So this should convince you that there is, in fact, some, smoothing going on. But when you kind of zoom out, you don't see it as much. Okay. However, the circularly symmetric guy doesn't get around the problem of the rippliness. And so, for example, again, if I make a very aggressive radially symmetric filter, then, here I get this kind of, rippliness that's a little bit more like a radially symmetric rippliness as opposed to just along the x and y directions. And the problem is that fundamentally what I have is a hard edge, and that hard edge is what's causing my problems, right? So kind of what I was showing before was, if I have a filter, let's see if I can do this right. So this is the kind of the footprint of my filter, and it looks like this, right? Either this or a footprint that looks like this, where I have a cylinder. I mean, either of these guys is going to lead to, so if this is the spatial, or this is the frequency domain, say ideal frequency domain filters. Either of these is going to lead to a time domain filter that has some sort of a, bounciness to it. And so this is called, I guess I've been calling it Ripley, but a better way to describe this in terms of image processing terms is what they call ringing. And so again, that ringing is exactly this phenomenon, right? So if I were to, again, make a radius 20 filter, right, this is the ringing phenomenon where I can see that edges in the image kind of throw off these, extra bumps. And those are, unfortunately, part of the, they're endemic to filtering with a hard edge, okay? So, on the other hand, life is good if we were to have a smoother edge in both the frequency domain and the time domain, right? And so, what we'd like to be able to do is remove this ringing. And so let me just make a note here. So kind of the summary of what we saw visually was, smaller filter cutoff in frequency domain. That leads to both more blurring, but also kind of bigger, more obvious ringing. Because in some sense, what would be the right word? Kind of like the period of the ringing, right? The distance that I see these things happening is proportional to, oops, right? So it's kind of the distance between these repeats is proportional to how aggressive my filter is, right? So if my filter is wider, these guys are closer together. You don't even necessarily notice them for small edges, right? Whereas if the filter is aggressive, you get these far apart rings, and that's like really obvious, right? So this is the kind of the phenomena that we're seeing. So one reason then that we don't like frequency domain filtering in general is that it produces these artifacts, right? So to avoid ringing, we often prefer simple spatial domain filters, right? So for example, let's go back to some of the filters we originally talked about, right? So if I have my good old friend of 1's 3 comma over 9, right? So that was our original smoothing filter, and I think I wrote another handy function for this. Right, so this function basically says, just show me what the Fourier transform of a filter's looks like. So if I do the Fourier transform of this filter, again, this now is the Fourier domain of that filter. And so there is, so again, this is a little bit confusing because before I was showing a color plot in the spatial domain, this is a color plot in the frequency domain. So this Fourier transform is like a kind of a nice, smooth thing. If I were to talk about like a, Fourier transform that is, actually this is just a symmetric thing from what we were talking about earlier, right? So actually, this is exactly the reverse of what I just showed you, right? So here, in some sense, a filter that is just ones is like a box in the spatial domain, right? So I expect a box in the spatial domain to give me something that is kind of like ripply in the frequency domain. So why don't we have a problem with what the image looks like? Well, the reason is that, again, for real images, there's not a lot of frequency content out in the range where this ringing is happening in the frequency domain. So anything is, there's not that much happening where that ringing is occurring, so we don't see a visual artifact, right? So if I were to look at the image filtered by, filtered by this guy, right? So here is a low-pass filtered image that doesn't have that kind of, ringing artifact because I've applied the filter in the spatial domain. And so, again, that's often what we end up doing is that we don't want to introduce these perceptual artifacts into the image. Now, we didn't really talk about in DSP that much, but I mean, in theory, the same artifacts occur when you are doing audio processing. Like if you had a box filter in the in the frequency domain for a 1D audio signal, you applied it to a song, you might hear some weird, like, echoing or repeated parts of the song, and that would be the audio manifestation of ringing, right? So, it's interesting that there's different ways that you perceive the artifacts depending on what kind of signal you're filtering, be it a music file or an image. Okay. Now, there's actually the best of both worlds, which is that it turns out that a good exception is the Gaussian low-pass filter. So we talked about Gaussians in various contexts, in probability and other places, right? And so here, what I could do is I could define a function like this, where I could say, here is a function that says, as a function of frequency, when I'm in the middle, I have e to the 0, which is 1. And then as I get further away, this number in the numerator of the exponent becomes bigger, and therefore I get kind of like this Gaussian roll-off in the frequency domain, right? And so it looks like a Gaussian here, and the nice thing is that a Gaussian in the spatial domain turns into a Gaussian in the time domain, or a Gaussian in the frequency domain. That's a really nice property of Gaussian distributions. And that means that I can have smoothing that is nice in both worlds. Okay? So for example, let's look at how that works. So here, I have a function that lets me do a Gaussian low-pass filter. And now instead of supplying the hard edges of the box, what I'm really supplying is the variance of this Gaussian. And so here, I can see that this is the effective fall off of the Gaussian, right? And it's easier to see, well, this is okay. So here's the original image. Here's the original Fourier transform. Here is my Gaussian filter. And when I apply it to the image, now I get kind of nice, even smoothing. So if I were to look at them side by side again, here I get the smoothing that doesn't have any of these ringing artifacts. And all I need to do is decide how much smoothing I want by controlling the radius of the Gaussian filter, right? So if I have a smaller radius, that means that I'm going to have a bigger domain in the frequency world, and that means I'm going to let more of the original image information through, and that means that when I look at the filtered image, I'm going to have, a smoother look to it, right? And on the other hand, if I make this image, or if I make this a lot bigger, then I get a really blurry image, but doesn't have that kind of ringing look to it, right? So no amount of radius will have those visual artifacts that I had before. I guess here actually I need to make this radius a little bit smaller to get at where we might have seen those artifacts earlier. Right, so here's maybe a comparable image to what we would have tried to do with a box filter. Instead, I get this blurry image that doesn't have any ringing in it. And so it turns out, and we'll talk about this a little bit more after the exam, maybe even after the second exam, that these Gaussian low-pass filters are very commonly used in image processing because they give us a nice, smooth, artifact-free, blurred image. And kind of what I'm seeing here is what does the filter look like as a spatial domain filter? And I can see that there is no, if I look at it from the side, it also looks like a Gaussian, right? And so this is a nice smooth filter in the spatial domain and a nice smooth filter in the frequency domain. And the bigger I make the cutoff in the frequency domain, the smaller the spatial filter is going to look like, right? So that kind of stands to reason, right? So imagine that the filter was really big, in the frequency domain, meaning that it let in all the frequency, that means I'm not changing the image very much at all, which means that the spatial filter should get closer and closer to just the identity, which is 1 in the middle and 0 everywhere else. And as I make the Gaussian filter smaller in the frequency domain, that means that I'm filtering more and more high-frequency edge stuff out, which means that my spatial filter should spread out, right? So if this is the spatial filter corresponding to a relatively wide Gaussian filter, if I were to let more in, right, I would get even a narrower, I'm sorry, if I were to make sure I'm doing this right. Now I'm wondering whether I defined this the wrong way. So here's my thing. 100 is the sigma of the blur in the, I guess I'm defining the blur here in the spatial domain. So the bigger my number gets, the more blurry the image gets. And so the more blurry the image gets, the more broadly the spatial filter spreads out. So actually, what I'm doing in my MATLAB command is I'm specifying the sigma for this spatial filter. So it looks really broad here, and then the way to think about it is in the frequency domain, it looks really narrow. So there's a duality between the way it should look in the frequency domain on the left and the spatial domain on the right. And so now if I were to make one of these things smaller, right, so if I was to make the spatial domain have a radius of 5, then I expect to see that the frequency domain gets bigger. Okay, so they do go side by side. I just was confused about what I was saying before. Okay, and so just a quick comment, how did I make this filter, right? So I mean, it was easy to make the ones thing that I used for low-pass filtering before. Again, there's a nice command in MATLAB that lets me make these special filters, and that command is called fspecial. And so again, here, all I have to do is ask for a Gaussian filter, here, like Gaussian low-pass filter, it's right there, and then it will give it to me, right? So if I say Gaussian of a certain size with a certain variance, it gives me that filter. So, for example, if I want a spatial domain filter that is Gaussian and I want it to be a, 11 by 11 mask with a variance with a radius of 2 pixels, I guess it's not very instructive, so if I do surf of this thing, yes, I did mean that. What? That doesn't look right. Oh, that's because, okay, so here's my h. If I do surf of h, right, I get this kind of simple, discrete approximation of a Gaussian filter. Okay. Okay. So, comments or questions about this? So far I've been doing all this stuff with low-pass filters, right? But you could also do high-pass filtering, right? And so there are a couple ways of doing high-pass filtering. Either we can do kind of the easiest way to do high-pass filtering is fundamentally to take, the identity and subtract a low-pass filter from it, right? Or more accurately, what I want to do is I want to take a filter that is not doing anything to the image at all, and this should be as big as whatever I want, and I subtract some low-pass filter from it, right? That's the basic idea, is that high-pass is identity minus low-pass, because low-pass plus high-pass adds up to the whole thing, right? And so, for example, if I took, this filter and I subtracted this filter from it, what I would get would be a filter that would be, negative around the edges, and positive in the middle, right? And as we discussed, that has an effect of finding edges in the image. And so again, we can do the same thing. So if I have a filter that's basically like saying exactly what I just said, right? So here's my, oops, I don't know why I keep on wanting to divide by 3. Here's my high-pass filter, and now I look at the Fourier transform of that. So here, this is dark where it's small and white where it's high, right? So here's a flat rendering of it, and here is a 2D rendering of the surface. And so I can see that basically this is like the two-dimensional analog of a high-pass filter, right? Because at the middle, at the DC value, it's 0, right? It's filtering out all the low frequencies, and it's keeping the frequencies around the periphery, meaning that, you know, it's got 1 kind of around these high-frequency areas. Sorry, I'm trying to rotate this the right way here, right? So more or less the filter is equal to 1 in high-frequency range and equal to 0 in low-frequency range. And again, since this is a small spatial filter, I'm going to get some sort of a Ripley frequency domain filter. I mean, I can't have, you know, except for Gaussians, I can't kind of have it smooth in both ways, right? So this is a small spatial domain guy, meaning I get a kind of Ripley frequency domain guy. And if I were to make a bigger filter or a different filter, so for example, we also talked about like a different low-pass filter might be something like something that weights the nearer neighbors more than the outer neighbors, right? So these numbers still sum to 1, but I'm giving a little bit more weight to the middle guy. And now if I have my identity filter, and I make a high-pass filter that is the difference of these guys, and I look at the frequency transform of that. So again, this actually turns out to be a little bit, you know, more ideal of a high-pass filter, right? You can see that it really does look kind of nice or nicer in the frequency domain, definitely filtering out the middle stuff and passing the higher stuff. Okay, and you know, in the same way, it's possible to, and I guess we can actually show, in the same way, it's possible to design a Gaussian high-pass filter. So again, I can substitute my, you know, low-pass filter. This could be, you know, also a Gaussian filter. And the effect of that would be something, again, that looks like kind of an inverted bowl. Kind of a crappy drawing, but you kind of get the idea, right? Something that is a bowl in the middle and big at the ends. And so let's take a look at some of that in terms of applying it to the image. So I believe that I made a little high-pass option for my ideal filter. So let's see. Gaussian low-pass, high-pass. I may not have made this, but let's see. So let's suppose that I want to show a high-pass filtered version of this image. So here, for example, here's the original image. Here's its Fourier transform. Here is the filter mask. Now this is saying, again, this is like a box filter that cuts out all the low frequencies, keeps all the high frequencies. And so basically, after I notch out all that stuff, my Fourier transform is going to look really weird, and my filtered image is going to look like just the edges of the original image, right? And again, this is the kind of thing that you might want to be careful about, because since this is, again, a sharp-edged filter in one domain, I get this same kind of ringing artifact even in the edge map, right? And so if I was going to use this to detect edges later on, for example, I might want to be a little bit careful about not wanting to detect these new ripples in the sky as being false edges, right? I wouldn't have this problem if I used a Gaussian filter instead. And I'm not sure whether I have, I guess I don't think I have a Gaussian high-pass filter here, but I guess I could make one, right? So let's make a Gaussian high-pass filter. So here's my Gaussian filter. It's 11 by 11. If I look at the maximum value of this thing, if I let's say that I scale this to be do this for a second. So let's suppose that I scale this so that I guess these things sum to 1 already, is that right? Oops. Hey, what's happening to you? Yes, okay, so these guys add up to 1, so that's okay. So then basically, if I were to make a 11 by 11 identity filter where the middle element was 1, and then I were to make a high-pass filter that is this identity guy minus this guy.
Should that be zeros?
All right. Hold on, I'll figure it out. All right, better. Okay, so now if I were to look at the surface of this guy, where did I go wrong here? Yeah, that tells me nothing. I'm disgusted. So this doesn't look quite what I was expecting to look like. Why is that? Let's think about this for a second. I guess part of it is that well, first let me make sure I got this right. So here's my spike in the middle. Oh, I think the problem is that my Gaussian values are all too low, right? So if I were to look at this, the maximum of this guy is pretty low, right? So kind of what I want to do is I want to make a filter that is, well, actually, hold on a second. Yeah, so these guys add up to 0. So maybe this is okay. Let's see what happens. So let's just apply this filter and see what I got. Only one way to find out what we did here. So let's take my image and let's filter it with this guy. Yeah, okay. Well, actually, that did what I wanted, right? It gave me the edges. Right, so I did okay. All right, I'm happy. So again, this works the way it should, right? Okay, so again, this fspecial command is a good place to look for all sorts of different filters. So one thing that we talked about, actually, before I go on this topic, we talked about this idea of the Laplacian filter. I thought I had some notes on this. Right. So when we started talking about filtering, we mentioned this idea of the Laplacian, which was basically a discrete version of the image. It's like the second derivative of the image. It's like saying, what happens if we add up both of these derivatives, right? We showed that this should respond strongly to edges, right? So it's like an edge detecting filter. And now if I want to know what does the Fourier transform of this Laplacian filter look like, well, so again, we kind of show what this looked like in the spatial domain. What should the Fourier transform of this thing look like? Well, we could use some Fourier transform properties. Back in the day, we showed, for example, that when I take the derivative of something, I take out, so again, this is kind of like an old signal and systems idea, right? When I take the derivative of something in the frequency domain, I multiply it by a j omega, right? Same kind of thing in the spatial domain, except now I have two frequency variables I have to keep track of. I've got a u and a v, right? So when I take the derivative here, what I expect to get is I get a ju squared times the original Fourier transform of the image. And here, I get a jv squared times the Fourier transform of the original image. And this turns out there's a whole thing where there's actually a 2 pi squared in front of each of these things. So when I put this all together, what I get is a 4 pi squared. The j's cancel out, so I have a negative, or the j's turn into negative 1s. Then I have a u squared plus v squared times the Fourier transform of I, right? So what this is telling me is that this here is the, basically the frequency domain version of the Laplacian filter. And so again, that's something that is 0 in the middle of the frequency domain and gets bigger like a quadratic as I go outside from 0, right?
Is that 4 pi or 8 pi?
Should be 4 pi, I think, right? Because I got a 2 pi squared here, so I get a 4 pi squared. And I get another factor here. Yeah, that should be right. And I believe I have this in my special guy here, too. So if I have a Laplacian, see how I defined it here. Yep, Laplacian. So here, I'm just defining that filter in the frequency domain here, where I give it a radius in both directions. So or this could be something that I never actually implemented, and it doesn't work. X. Well, again, let's not make this hard. Let's not make this any harder on myself, because there's a Laplacian here that gives me a, gives me a Laplacian shape. So if I were to say H equals F special Laplacian, and now I were to look at the Fourier transform of this guy, I see that indeed it does look like a parabola that, keeps on going up. And again, the only reason this doesn't look like a total parabola is because it's getting cut off by the edges and because it's an approximation to the true Laplacian. Okay, so homework for this short homework is basically just having you do some of the things I've just been showing you on your own. Okay, so as you can see, it's all just manipulations of these same few MATLAB commands. Okay, so now I want to just kind of switch gears for 1 second and mention a few words about sampling and aliasing in the frequency domain, right? So basically, just like in 1D, we have to deal with terms like, sampling, that's not a word, sampling, aliasing. We have to know what it means for a signal to be band limited, right? So all that kind of, Nyquist, all this kind of terminology applies to image processing as well, right? So, for example, a 2D function, also known as an image, is band limited if its Fourier transform is 0 outside some rectangular region. That is, the Fourier transform is identically equal to 0 for, certain spatial frequencies in this direction and spatial frequencies in this direction. So basically, that means that I can contain the Fourier transform of a signal inside this box entirely. Okay? And by the same token, there is a two-dimensional Nyquist theorem that says that as long as I sample the image at twice the Nyquist frequency in both directions, I won't observe any aliasing in the resulting image. Okay? So, that kind of stands to reason. If you don't do that, then you get this kind of spatial aliasing. Okay? So, for example, suppose I had a checkerboard that was like a fine checkerboard, right? That's a fine checkerboard. right? So if my pixels of this image were, so these are not pixels, this is actually just a picture of a black and white continuous time checkerboard, right? So if my pixels are small enough, right, and they're sampling along here, well, then I don't have any problems with aliasing at all, right? I've got, you know, I've got at least 2 pixels in every checker, right? Whereas if I were to sample like too infrequently, like sample here, sample here, sample here in both directions, well, then what looked like, you know, what actually is underlyingly this high frequency checkerboard would be sampled to look like a constant black image, right? That would be like a spatial version of aliasing. So all this to say that you have to sample faster than the highest frequency details in your image, right? And so in some sense for image processing, there's not that much you can do about it in the sense of, you know, your camera probably doesn't have that much control over the resolution, or at least you don't fool around with it that much, right? So I mean, and you're also probably not taking pictures of like super tiny text on surfaces. So in some sense, aliasing is not something that you can do much about after the fact. Either you have it or you don't, and you've lost some image details that you just weren't able to resolve. But we can, you know, there are some similar ideas. So one thing that you hear a lot about is anti-aliasing, right? Especially if you guys are video game players, right? And so anti-aliasing is not, the term is kind of misleading. It's not that you take your acquired image and you do something to it and then it gets better, right? Once you've got an image that has got aliasing in it, you can't do anything to undo it, right? So the way I think about this is that, you know, it's not removing aliasing. From an existing image. It's basically blurring a digital image prior to resampling to avoid visual artifacts. Right? So what I mean by that is that, you know, suppose I need to downsample an image. What I would do is I would take my original image, I would put it through blur or a low-pass filter to get my result, and then I would downsample this image. And so why do we do that, right? So when we took DSP, we talked about sampling, upsampling and downsampling, right? What's happening in the frequency domain when I downsample an image is the following, right? So if this is my frequency domain version, and again, this is kind of like the throwback to our DSP class, right? So if this is what the Fourier transform of my original image looked like, and now I downsample it, what happens is that these copies shrink and spread out. And this is where things can go wrong, right? So when they spread out, I can get this aliasing where low frequency stuff in the original image turns into what appears to be high frequency stuff. And so what I could do instead would be to say, okay, prior to downsampling, I'm going to apply a low pass filter to the image to make sure that when I do downsample, I have basically no overlap. So I mean, in some sense, I've already cut out some high frequency information that I wouldn't be able to resolve anyway, but I have avoided any sort of, you know, additional artifacts by having low frequencies mixed in with high frequencies, right? So this is exactly the same concept that we talked about in DSP, and so we can go back and look at that lecture for what happens when I downsample a signal, okay? And so here's a kind of an example of that in MATLAB. So here is a test image. This is a famous image processing test image that is, I think it's mainly used because this woman is like wearing stripy pants and she's in a rattan chair and there's a stripy tablecloth and there's stripes in the bookcase. So this is a good example for the way things can go wrong when you downsample an image, right? So here, she's got these stripy pants, right? And this is a case where I've got this high frequency component in the image. So if I were to downsample this image, I might have some problems, right? So if I were to say, let's take every 4th pixel of the image, right? That's like downsampling by a factor of 4 in both directions. And if I look at this picture, so you can see that what used to look like vertical stripes on the pants have now kind of turned into horizontal curvy stripes on the pants, right? That's a manifestation of spatial aliasing. So here, for example, these stripes are not close enough together to cause a problem when I downsample, but these stripes are too fine to do that, right? And so what I should do to mitigate this phenomenon is to blur the image a little bit first before I downsample. And so what I could do, for example, is say, okay, I'm going to take my, I'm going to take a filter like, where was that nice one I had? I had a good filter. It was like the, yeah, this guy. So now if I were to take the filter of this guy, so this is going to be a blurrier image, right? And so in some sense, it doesn't really look very blurry at all, does it? This may not be blurry enough. If I were to downsample this, what would I see? Same problem. So I don't think I blurred this enough. Let's try instead using a filter that is, say, this guy. Right. So here, this is kind of the phenomenon that I get. Right. In some sense, I am pre-blurring out the frequencies that I know are going to be problematic for me later. Right. So I'm losing those high frequencies either way. Either I'm going to blur them out beforehand, or I'm going to have them corrupted when I downsample if I didn't take care of it. But now if I were to downsample this image, I shouldn't have any problem, right? So here, the downsample version doesn't have any of these artifacts in the pants, but at the same time, it doesn't have any, it doesn't have the same kind of stripiness either. Because I couldn't obtain that anyway. So this is kind of like the trade-off. And of course, I'm being really casual about this because in theory, right, if I go back to my drawing here, in theory, I should know exactly what band edge I want the low-pass filter to be at to be just as big as I need to prevent that aliasing, right? So I could have really tried hard to match the edges of my low-pass filter to the downsampling rate that I had, right? And here I was just being I was just throwing low-pass filters at the problem without really thinking about how wide they were in the frequency domain. I could do better than that, but I decided not to. Okay, but that's the idea. And let me just also mention, so what is anti-aliasing in video games, right? So there are lots of kinds of anti-aliasing, and of course there are lots of people who will tell you about, why different kinds of things are better. But anti-aliasing, there are many different kinds. Has many flavors. Right. So one of the stupidest things that you could do, which is not the way that I think most anti-aliasing works, is that suppose that I've got a low resolution display. Okay, so suppose that I've got a 1920 by 1080 display, right? So one way that anti-aliasing is often used, not only for video games, but also for things like fonts on screens, right? So for example, I don't think I have a great example of this here. What was that image that I used for the homework with the letters on it? I forgot what I called that image that had all the test images on it. Maybe I didn't even actually. Sorry, hold on one second. Yeah, there was that one test image that I was trying to find, the one that had the letters on it. Basically, one thing that you often see in, say, also for text, right? Because the problem with text is that, suppose I have some sort of like, ideal letter. You can tell I'm not a font designer, right? So suppose that I have like a nice black and white letter A, right, that I have designed in my font, right? And now if I were to sample this too coarsely, right, what I would get would be some kind of crappy pixelated A, right? Because direct sampling means that I'm either only going to hit black or white at every pixel, right? And so the result of sampling that black and white font is going to be a really crummy looking thing. What I really would like to do instead would be to get like shades of gray in these pixels that are, you know, not right on the letter, that kind of give me some sense that the letter is fading into the background, right? And the same thing I think in video games, right? So if you have a straight line, like a very fine wire, for example, in a video game, if you're not careful, that wire will manifest itself as kind of like this jaggy, pixelated thing on the screen, right? So what is the solution? The solution is, or one solution is to say, okay, if your graphics card and processor are up to it, what I should do is I should say render this at 1920 times 4 by 1080 by 4, right? So in the background, I'm making this massive image. And then at every pixel on this image, what I do is to say, and then I downsample each, 4 by 4 square. So for example, I could average inside each square to get, each pixel. Right, so instead of every pixel taking its color from exactly one point on a surface in the world, I take a very, very high resolution image out in the world that I never rendered to my screen, and I downsample that, and that's what I show you on the screen. I downsample it by blurring and then sampling, right? The blurring is like, for example, averaging the pixels inside that square, right? So, obviously your computer has to be really up to the task of rendering much, much higher resolution images inside the processor before it decides what to show you on the screen. So, that's why there's a big difference between like 2 times anti-aliasing and 4 times anti-aliasing and so on. And this is a very crude approximation of what actually happens inside the computer. Like if you look at the, there are game blogs that are dedicated to, what if you did this kind of anti-aliasing and that? There's like 10 different flavors of doing it, right? But they all come down to something like this, where you have a high resolution thing that you are then blurring and downsampling to get the low resolution thing. And so, for example, this could make a good project idea. So investigating and implementing different kinds of downsampling that would normally occur in your graphics card hardware that you could try doing in MATLAB, for example. So that's not a bad project idea. Another thing that you can interpret as a kind of an aliasing problem is what are called Moire patterns. And so this is kind of a combination of kind of a sampling issue and also kind of a human visual system issue. So here's just a quick MATLAB demo to show that. Okay, stop this. So what you're going to see here is some lines that are the same distance apart. So let's just see here. Oops. Okay, so initially, maybe I should actually introduce this with paper and pencil first. So Moire patterns. The idea is that, let's suppose that I take, a grid of lines that is up and down, a fine grid, and then I add to that the same grid rotated by theta degrees. So this is grid, and this is grid rotated by theta. Right? So in some sense, there's only one fundamental, well, I guess there's kind of one fundamental frequency in this direction, one fundamental frequency in this direction. And so as I rotate things around, I really shouldn't be changing the frequency content of things. But visually, I get these very distracting patterns. And so if I were to do this example, what you're going to see is, first, the two grids are going to be aligned exactly. And then I'm going to start to turn one of them, right? And as I turn them, you start to see these dark and light alternating patterns of different frequencies that come from kind of coincidental alignments of dark and light pixels, especially at the corners of edges, right? So here you can see there's this kind of very strange and unpredictable, visual manifestation of where those so-called beat patterns occur, right? So here we're getting to the point where the images are perpendicular to each other, right? And then this looks, again, just like a normal grid. But certainly on its way there, you see these kind of strange, periodic patterns that are introduced by just the way that these, that these pixels of black ink add up, right? So I'm not really sure what I would call this, whether this is an aliasing thing or a sampling thing or a human perception thing. But it definitely is an issue, right? And again, it's the kind of issue that you could mitigate by, for example, low-pass filtering prior to rendering these images together. Okay. So I think with that, I'm done. Any questions? All right. So let me shut this down for a second. And just as a reminder, the